Hello. So welcome to lecture number 4 on electrical circuits 1. So today we are going to discuss the topic that is passive elements. The elements are resistor, inductor and capacitor. So passive elements. So first we will discuss about the resistance parameter. So first we will see the background about this one. So what is the property of a resistor and how the symbol is came, and what are the voltage, current, power and energy relationship for this resistance we will see now. So when current flows in a material, so free electrons move through material and collide with other atoms. So what is the point here? So current flows into a material, so the free electrons are moved through a material and collide with the other atoms. So like we can see, let us take one simple material here. So here when current is passes through this, then the free electrons move through a material here. So before that the electrons will be in random in nature. So when we are applying the current flows to this material, so these electrons will hit the other atoms in that material. So when it hits the other atoms in the material, so these atoms will again release the electrons. So again these electrons will hit the other atoms. So like that, so the collisions will be causes. So this collision of electrons lose some of their energy. So this loss of energy per unit charge is the drop in the potential across the material. So that means here, if you can see here, if you are applying one electric field to this material, then current starts flows into this material. So then when current flows into the material, free electrons moves through the material and collide with the atoms. So these atoms again release the two electrons, and the two electrons again hit the other atoms. So then what happens, the collisions will be increases. So these collisions causes electrons to lose some of their energies. So whenever the collision is causes here, so these electrons will lose their energy. So once they lose the energy, it will lose some energy. So this loss of energy per unit charge, we can in the drop is the potential of the material. So potential across that material. The large amount of energy lost by electrons is related to physical property of the material. So these collisions restrict the movement of electrons. So whatever the electrons are there, so these are hit the other atom, so again these are hit with another atom. So they really whenever these hit the other atom, so they will lose the energy. So like that, this process is continuous, and they restrict the flow of movement of electrons at a particular time here. So that is a property of a material. So here the property of a material to restrict the flow of electrons is called resistance. So that is a main property of a resistor. Then the symbol came like this here. So that is a symbol of the resistance. So the property of a material to oppose the flow of electrons is called resistance. So it is denoted by capital R. So usually the symbol, we can say, you can denote the resistor symbol here. So this is the symbol of resistor. So the units of this resistance, so we can measure this resistance in ohms, and it is represented as capital letter R. So ohm is defined as, so the resistance offered by the material when a current of 1 ampere flows between two terminals with 1 volt applied across it. So that is the ohm definition. So ohm definition is saying that, okay, so this is the current flows into this material. So defined as the resistance offered by the material when current of 1 ampere is flows between the two terminals when 1 volt is applied across it. If we can apply 1 volt here, 1 ampere of current is flows here. So then it is defined as it will oppose the flow of current. So that we can call it as a ohm. So according to Ohm's law, so current is directly proportional to the voltage and inversely proportional to the resistance of the circuit. So that is current I is directly proportional to the voltage and inversely proportional to the resistance according to Ohm's law. So therefore, so the current I is equals to V divided by R, or if you can say that the 1 by R is nothing but conductance of the conductor. So that is 1 by R is nothing but G, so that is nothing but conductance of the conductor. So therefore current I is equals to G into V. So the unit of conductance is mho. So now when current flows through the any resistive material, heat will be generated, so by the collision of electrons, so with other atom particles. So the power absorbed by the resistor is converted into heat. So here the resistor is absorb the power and dissipate the energy in the form of heat. So now let us see the power and energy relations. So before that, we will see the what is the voltage and current relations across this resistor. So that is V is equals to I into R, and from this I is equals to V divided by R. So now the power absorbed by the resistor is given by, so power P is equals to V into I. So that is if we can substitute the voltage value, so in this expression, so that is V is equals to I into R. So that is I square R, which is nothing but I square R watts, R, so that is P is equals to V into I. So if you can substitute V here, so V is nothing but I into R into I, so that is nothing but I square into R watts. Similarly, if you can substitute this I value in this expression, that is V into I is nothing but V divided by R, so that is V square divided by R watts. So this is the power absorbed by the resistor. Next one, energy lost in the resistance in a time t is given by. So energy is nothing but the integration of power over a period of time. So that is power P is equals to integration of power into dt. So that is, so P into T, so where P is nothing but I square into R, so power into time. So if we can take the power is a constant outside, so differentiation integration cancel, so we are getting as P into T. So power P is equals to I square into T or V square by R. So this is the power expression. So the power can be measured in joules or watt hours. So power can be measured in joules, or we can also say that watt hours or kilowatt hours. This energy can be measured in joules or watt hour or kilowatt hour or megawatt hour. Similarly, the power can be measured in watts or kilowatts or megawatts. These are the units of power, these are the units of energy. So that is about the voltage, current, power and energy in the resistance parameters. So we will see the different types of resistors here. So we are having the different types of resistors. So linear resistor, non-linear resistor, fixed resistor, variable resistor, thermistor, light dependent resistors, varistor resistor, thermistor, rheostars, potentiometer. So these are different types of resistors are used for different applications in electrical engineering. Okay. So next we will see the next topic is the inductance parameter. So here, before discussing about the inductance, so first we will see what is inductance. So here, a wire of a certain length, when twisted into a coil, it will become a basic inductor. So that means here, if you can take a wire of this length and we have to twist it into that wire in this fashion, so then it will become say coil, basic inductor, we can say it's inductor. So if current is made passed through this inductor, then an electromagnetic field is formed. So that means here when the current is made pass to this inductor, so then electromagnetic field will be established or electromagnetic field will be formed in this inductor. So a change in magnitude of current changes the electromagnetic field. So that means here, if we can change the current here, then electromagnetic field, that is electromagnetic field is also changes. That is flux is, we can say that the electromagnetic flux will also changes. So increase the current, so expands the magnetic field, and decrease the current and decrease the electromagnetic field, and it reduces the electromagnetic field. So therefore, change in current produces change in electromagnetic field. So which induces a voltage across this coil according to the Faraday's laws of electromagnetic induction. So that means here, this current, we can say whatever the current is passing here, so that current is responsible for production of flux, and this flux is again production for the EMF induced in a coil, and this EMF is again oppose the flow of this EMF is again oppose the main field here, so that is cause for production of it according to the Lenz's law. So the unit of inductance, we can denote a unit, we can denote as a Henry, and it is denoted by H. So it is the inductance, we can represent it as H. So that means here, so the unit, the symbol of this one inductance is this one, and it is given as L. It is represented as a capital letter L, and the units for this inductance is Henrys. Henry. So by the definition, the inductance of 1 Henry, when a current through the coil changes at the rate of 1 ampere per second, induces 1 volt across a coil. So this is the definition of inductance. So the symbol of the inductance, it is given as like this. This is the symbol of inductance. So what is the definition of inductance here? So inductance is nothing but 1 Henry when current is passed through coil. So when current is passed through coil, so changes at a rate of 1 ampere per second. So that is, it changes at a rate of 1 ampere per second, induces a voltage across the coil. So that is nothing but inductance of a coil. So that is, it is given as L, and the units for this one is L. So that is, we can see if the voltage is directly proportional to the di by dt. So if we can remove the proportionality constant, then we are getting as V is equals to L into di by dt. So this is the symbol, and this is the voltage current relations. So if you can write the above equation, so then it is so that is V is equals to L into di by dt. So we can write here that is V is equals to L into di by dt. So from this we can write as di is equals to 1 by L into V into dt. So if we can integrate this expression on both sides, then we are getting current I is equals to 1 by L integral V into dt. So if we can integrate this into the period of from 0 to t, so that is, so if we can expand this one, then we are getting as, so that is I of t minus I of 0 is equals to 1 by L integral 0 to t v dt. So take this negative term to right hand side, so then I of t is equals to 1 by L integral 0 to t v dt plus I of 0. So this I of 0 is nothing but the initial current in the coil. So from the above equations, we can say that, we can note that current in an inductor depends upon the integral of the voltage across its terminals. That is the first point. And the initial current in the coil. So these are the voltage and current relations in inductor. Now coming to, we will see the next one is the power absorbed by the inductor. So the power absorbed by the inductor, that is power P is equals to V into I. So V is nothing but L into di by dt. So what is V here? V is nothing but L into di by dt. So that is, so power P is equals to L into di by dt into I. So I can write this I in here. So that is, so this much of watts. So power P is equals to Li into di by dt. So similarly, energy stored by the inductor is given by. So in energy stored by the inductor is given by, so that is integral 0 to t p dt. So what is power here? Power P is equals to L into I into di by dt into dt. So here dt will gets cancelled. So take L is a constant term, so take outside. So integration of this I with respect to I, then we are getting as I square divided by 2. So this is the energy stored in inductor, so that is half Li square. So the energy stored by the inductor is given by half Li square. So this is the joules or watt hour. So from the above discussion, we conclude that, so here we have some of the points we have to summarize about the inductor. So the inductor induced voltage across the inductor is 0. So first point is induced voltage across the inductor is 0. If the current through that it is constant. That means here, so according to the relation we will talk here. So V is equals to L into di by dt. So according to this relation, if we can pass the current through that is constant current. If we can take this is constant current, it is flows here. So then induced voltage across that inductor is 0. So that means here V across the inductor is 0, because if you can pass a constant current. So constant current means DC current. If you can pass to the inductor, then voltage across that inductor is 0. So that means inductor will act as a short circuit to the DC. That is the first conclusion. So for inductors will act as a short circuit for DC. Similarly, so if a small change in a current within a 0 time, so through the inductor, which gives the infinity voltage across the inductor. So that means here, if you can see here, if you can pass a very small, change in current within 0 time. So within 0 time means if we can t is equals to 0, so then we are getting that infinite voltage we are getting. So that is voltage across this inductor we are getting as infinity. So physically it is impossible. So that's why fixed inductor current cannot change abruptly. So that's why in a fixed inductor, so the current cannot be changed abruptly. Next point, so inductor can store a finite amount of energy even if it is voltage across inductor is 0. So even if the voltage across inductor is 0, so it will be stores the energy in the form of magnetic field. So the inductor will store the energy in the form of magnetic field. So pure inductor never dissipates energy, then it only stores it. So pure inductor, if you can take, the pure inductor will never dissipate the energy, it can only store it. So that's why it is also called non-dissipative passive element. So physically inductor will dissipate power due to the internal resistance. So because of the internal resistance, every inductor is not getting pure, so it is having some internal resistance also. So this is the practical inductance symbol. So because of that internal resistance, so this is our internal resistance. So physical inductor dissipates power due to internal resistance. So these are the points regarding the inductance. Okay. So these are the types of inductors. So the first one is air core inductor and iron core inductor, ferrite core inductor, fixed inductors, variable inductors, radio frequency inductors, power inductors, and choke inductors, toroidal inductors. So these are the different types of inductors we can use for different applications. So like in electronic circuits and electrical circuits, we can use these different types of inductors. Next, coming to the third one, that is capacitor parameter. So capacitor, before discussing the capacitor parameter, so first we will see what is the capacitor. So capacitor is a it is a two conducting plates, two conducting surfaces separated by an dielectric medium. So this is the dielectric medium separated by insulating medium, exhibit a property of a capacitor, then we can call that as a capacitor. So the conducting surfaces are, these two are electrodes. So these are the electrodes, and insulating medium is called as this is the dielectric medium. So this is dielectric medium. So these are the capacitor plates. So it is separated by a dielectric medium. So here the capacitor will store energy in the form of electric field. So that is established between the opposite charges on the two electrodes. So how the capacitor will stores energy means we will see here one simple explanation here. So first we will see. So initially capacitor plates are under neutral conditions. So if we can apply voltage to these capacitors, so we can say that initially these plates are under neutral conditions. So let us take these two plates are on neutral condition, and these plates are having positive and negative charges. This is under neutral condition. So if we can apply voltage across these two plates here, then electrons in the one plate is attracted. So these electrons will move to the positive plate, and this negative voltage again pushes back to this voltage here. So there all the negative electrons will be accumulated here, and over a process of time, so all the positive charges are accumulated here. So then what happened here? So then electric potential will be created, or electric field will be created between these two plates. So because of these are the electric field lines. So that's why the capacitor will stores the energy in the form of electric field, so that established by opposite charges of the two electrodes. So the electric field is represented by lines of force, just now we saw here, between the two positive and negative charges, and it is connected within the dielectric. So that is the point here. So therefore, the amount of charge per unit voltage is nothing but the capacitance. So that is capacitance C can be represented as, so the amount of charge that can be stored per unit voltage. We can call that as a capacitance of a capacitor. So it is denoted by C, and the units of the capacitance is Faraday, and it is denoted by F. So the units of capacitance is F. So sometimes we can represent as microfarads, millifarads. Okay, so these are the units of capacitance. So by the definition, we can say that 1 farad is defined as the amount of capacitance when 1 coulomb of charge is stored with 1 volt up across the plates. So the symbol for this capacitance we can represent here. This is the symbol of capacitance. So now coming to, we can see the relations for voltage, current, power and energy of capacitance also. So first we will see the capacitance definition. So the capacitance is C is equals to Q by V. So the amount of charge that can be stored for 1 volt if you are applied. So from this relation we can write that is C is equals to Q by V. So therefore, so Q is equals to C into V. So current, so from this we have to first write the relation for current. So current I is equals to dq divided by dt, that is rate of flow of charge. So if you can substitute this Q value in this current expression, then current I is equals to d into CV divided by dt. So from this we can take the C constant common. So that is C is equals to dV divided by dt. So therefore current flows into the capacitor is equals to C into dV divided by dt. Now let's derive the voltage across the capacitor. So the voltage across the capacitor. So from this relation only we can derive here. So take dV here. So that is dV is equals to 1 by C into I into dt. So now we have to integrate on both sides. So then we are having that relation as, so integration from 0 to t. So that is dV 1 by C integral 0 to t I dt. So if you can expand this one, then you are getting as, that is V of t minus V of 0 is equals to 1 by C integral 0 to t I dt. So therefore V of t, that is voltage across capacitor, is equals to 1 by C integral 0 to t I dt plus V of 0. So this V of 0 is nothing but initial voltage present in the capacitor. So this is about the voltage relation. So this is about the current relation. So let us take this is equation 1, equation 2. Now we will see the power relation. So power P is equals to the power absorbed by the capacitor is given by P is equals to V into I. So what is I? I is nothing but C into dV by dt. So what is power? Power P is equals to V into I. So that is C into V divided by dV by dt. So substitute this I here. So then that is C into V divided by dt. Next one, energy stored in the capacitor, that is W is equals to the integration of power over a period of time. So that is equals to integral 0 to t C into V into dV by dt into dt. So here dt cancel here. So then take C common here. So that integration of V is nothing but V square divided by 2. So therefore energy stored in the inductor is equals to half CV square. So from this above we can conclude that from the above discussion. So let us take the first conclusion. So along with the equation, that is current flows to the capacitor is equals to C into dV by dt. So if you can pass the constant voltage to the capacitor, if you can apply the constant voltage across the capacitor, then current flows into the capacitor is 0. So that means here, if you can apply the constant, that is DC voltage across the capacitor, then current flows to the capacitor is 0. That means here the derivative of constant is 0, therefore current I is equals to 0. When current I is equals to 0, so it will be behaves like as a open circuit. So that means here for the DC circuits, the capacitor will behave as open circuit. Capacitor will act as a open circuit. Similarly, if you can see that a small change in the voltage across the capacitance, that is C into dV by dt. So within 0 time, that is t is equals to 0. So we are getting the infinity current flows to that one. So which is practically impossible. So that's why for a fixed capacitor, the voltage cannot change abruptly. So here for a fixed capacitance, the voltage cannot change it abruptly. So therefore, capacitor won't allow sudden change of voltage. Previously the inductor is also we have seen, so inductor is also won't allow sudden change of current. So here from this conclusion what we have to take, the capacitor won't allow sudden change of voltage. So capacitor can store only finite amount of energy even if the current flows through it is 0. So therefore capacitor will never dissipate energy, but it can only stores the energy. It cannot dissipate the energy. So this is this is also called a non-dissipative passive element. So however, the physical capacitor will dissipate power due to the internal resistance. So capacitor is also having its internal resistance. So because of this internal resistance, the physical capacitor will dissipate power due to the internal resistance. Okay. So now we can see the different types of capacitors here. So these are the different types of capacitors. So each capacitor here you can see that they are mentioned the voltage rating and the farads and also the ampere hours also they are mentioned, watt hours also mentioned here. So this is the super capacitors. These are the tantalum capacitors, ceramic capacitors, so film capacitors, polyester capacitors, polypropylene capacitors, and silver mica capacitors, and variable capacitors. So these are the different types of capacitors that we are going to see. So these are the three different parameters that we have discussed for today's class. So that is resistor, inductor, and capacitor is completed. Thank you very much.